So we finished up on Wednesday talking about the measurement of matter, specifically how to estimate measurements in the lab. What was that rule again? We look at the hash mark and then what do we do? Go one digit further than the hash mark, right? So if you've got a ruler that shows the tenths place, you want to estimate to the hundredths place. So that's a really important rule, and we're going to talk about that more today. But let's briefly review these physical properties that we measure. We can measure length, mass, volume, temperature, time, current, intensity of light, or amount of things. One thing I am going to talk about today is temperature. Temperature is a little bit weird. You notice that SI unit, Kelvin. Most people aren't familiar with it. You don't see that unit on the news anywhere. So let's talk about temperature and energy. So temperature is a measure of hotness, right? Or heat is another way of thinking about it. Oftentimes people get this confused. They say, well, can't you measure cold too? Well, cold's just the absence of heat, right? You can't measure coldness directly, but you can measure hotness directly. That's really important when you get further up into chemistry and physics. We measure heat. We don't measure coldness of things. Energy is different than temperature, but they're somewhat related. How do we define energy? It gives us the ability to do what? To do work, right? So energy is the ability to do work. We can convert temperature or heat energy into usable energy, so we can cross these two over. They're closely related concepts. So let's talk about temperature. Temperature, we said we can measure in Kelvin or Celsius. These are both acceptable units, and it's a little bit confusing. I'll make a note that this is common for physics. And then Celsius is a little bit more common for chemistry. So for example, when we go into lab and I give you a thermometer, the thermometer won't have that temperature listed in Kelvin, it will be in Celsius. However, there may be situations where we need to convert these. So let's come up with the formula. Kelvin is Celsius plus 273.15. It's a pretty simple conversion. It's a relatively easy one to remember, and you're going to need to know it if you go on and take general chemistry. It's one of those numbers you just have to remember. What happens at 0 degrees Kelvin? Does anybody know?
Absolute zero.
Absolute zero, right? 0 degree Kelvin means that there is no heat in the system. There is no energy in the system. Basically, matter stops behaving like matter. It's a very bizarre thing. In fact, a group of physicists a couple years ago was able to cool a cluster of atoms down really, really close to absolute zero, and they were able to make something called the Bose-Einstein condensate, and they won the Nobel Prize for it. Super weird stuff, way out there physics, though. Normally when we're measuring things way above absolute zero. Yep.
How close have we gotten to 16 degrees? Something like that?
Oh, we've gotten way closer than that. We've gotten, I think, within like a billionth of a degree of absolute zero. Yeah, it's weird to think about. So on Earth, we've created the coldest spot in the solar system and the hottest spot in the solar system. It's weird to think about, but humans are pretty clever. All right, energy is a little bit different. We measure energy in joules oftentimes. Again, joules are really common in physics. What's really common for chemistry or with food? Calories. And actually, let's be careful to make this a little c, and I'll explain why. Whoop. So joules are the SI unit. However, like I said, calories are really common even in chemistry. and just on food products in general. There are some conversion factors though. 1 calorie is equal to 4.184 joules. Another way of defining a calorie is that it is the energy required to raise the temperature of water, specifically 1 gram of water, by 1 degree Celsius. So we're able to convert these pretty easily, and if you go on and take general chemistry, you'll talk about things called bomb calorimeters, where we can actually measure the amount of energy contained within chemical bonds. And we do that by basically measuring the increase of water temperature. There is one important note, though, that the calorie that we're measuring in chemistry is oftentimes very different than food calories. So a food calorie is always spelled with a capital C. This is equal to 1,000 calories with a small c. So that capitalization matters a lot. If you look on food packaging, it's always a capital C, which means it's enough energy to raise 1,000 grams of water by 1 degree Celsius. It's a lot more energy than the little c. This is also 1 kcal. So if you go to Europe and other countries, to avoid confusion, they just call it a kilocalorie. It's the same thing as calorie with a big C. Any questions about that? All right, so oftentimes when we're measuring things, we have to do math, and we have to be very, very careful with the number of digits that are included, similar to yesterday where we had to be careful of the number of digits included when we were measuring in lab. So let's take a look at this. This is called significant figures or significant digits. And I've got a list of rules for you guys. The first one is that all non-zero numbers are significant. And so I'll show you guys what I mean. How many significant digits are in 423? 3. We don't even have a 0 in there, so it's got to be 3 significant figures. Okay, that's pretty easy. Second one is all zeros between non-zero numbers are significant. And again, I'll show you an example. Let's say we have 103. How many significant figures are there? 3, because the 0 is between 2 non-zero numbers. We still count it, right? So in this case, there's 3. This is counted. People oftentimes get that mixed up. They think that any 0 doesn't get counted. That's not always true. All right, the next one is that all zeros which are to the right of a decimal are significant. Actually, I should be more careful when I say that. I'll put an and at the end of the number. So let's do some of these examples. So the first one is 0.00010. Question is, which zeros are significant? Are the ones up here significant? No, because they're not at the end of a number, right? We do have a decimal, but these are at the beginning of the number, so these aren't counted. So do not count. However, this is at the end. And there is a decimal. So it counts. You do have to be aware of that decimal. If there's no decimal, the rules change a little bit. All right, one last rule. This is rule 4. All zeros left of a decimal and in a number greater than 10, or I should say greater or equal to 10, are significant. All right, so let's do some more examples with these. Let's say we've got 10.0. How many significant digits should be counted? What do you guys think? Would it be 1, 2, 3? It's not going to be 4. So in this case, we actually have to look at Rule 3 again. So Rule 3 said all zeros which are to the right of a decimal and at the end of a number are significant. That means that this one is significant. And if we look at this one, that is to the left of your decimal, and it's in a number greater, or I should say equal to 10 in this case. So this one is also significant. And I'll just put Rule 4, and over here I'll put Rule 3. These can be a little bit tricky when you're getting used to them. So in this one we do have 3 significant digits. Let's do another one. So this is 1,000 with a decimal. The decimal in this case actually does matter a lot, whether or not you show it with a decimal or without. So what do you guys think? How many significant digits will this have? We've got zeros to the left of the decimal, right? So they're counted. That means we count all of the digits, including the 0. So we'll say this has 4. And we count these due to Rule 4.
Oh, wait, so if that was just 1,000 without the decimal, there would only be one significant number?
Oh yeah, that was my next question. You're stealing my thunder. So 1,000 without a decimal, do we count those zeros? No, there's no decimal shown. So in this case, this only has one significant digit. This matters a lot, right? That decimal basically indicates the degree of precision that you had with your measurement, right? We need to show whether or not we were estimating to the ones place or if we were estimating to the hundredths place, right? We need to clarify that. Otherwise, you're going to be really confused. Let's do a few more examples, and I'll give you guys some time to work on this. We'll do 4, 8, 9, 2, 3, 3.967, 900.06, and 0.0004, and then 8.1000, and then 501.040. So I want you guys to tell me the number of sig figs here. And I'll give you guys a minute to work on it, and then check with your neighbor too and see if you agree. If you feel pretty confident too, you can give me a thumbs up. Let's do the first three really quick. I think the first three are a lot easier. The first one, we don't even have a 0. It's got to be 5, right? Not too bad. Next one, same sort of thing. Even though we have a decimal, we don't even have zeros, so it's got to be 4. What about the next one? 5. We count all the zeros between non-zero numbers. Then we get into the trickier ones. Does anybody want to help me with this next one? Why do you think it's just 1? Why don't we count the zeros to the left? Yeah, exactly. If we go back up and we look at our rules, we said all zeros which are to the right of a decimal and at the end of the number are significant, but the ones at the beginning of the number aren't, so we don't count those. So rule 3 says that this next one should only have one significant figure. What about the 8.1000? Do we count the zeros at the end? Yeah, they are to the right of the decimal and at the end of the number, so we would have 5 sig figs here. And then what about the next one? 6. We've got zeros between non-zero numbers, and we've got a 0 at the end of the number, and there's a decimal, right? So not too bad.
So for the 3.967, you would count all of them because there's no zeros?
Exactly. All non-zero numbers are counted as significant. Yeah. So let's take a look at some of the math rules when you're dealing with sig figs. And I'm just going to abbreviate this as sig figs. Okay. The first one is for addition or subtraction. And the rule states your results cannot be more precise than your least precise measurement. And I'll show you guys what I mean by this. So let's take an example. Let's say we have 23.112233 added to 1.3324 added to 0.25. I'm going to go old school addition and stack them, right? Which numbers are least precise? Is it the top one, the middle one, or the bottom one? Bottom one. We were only confident to the hundredths place. In the bottom one, where the top ones, we were confident to a much higher degree, right? So this is only precise to the hundredths place. Okay, so when we go ahead and we add this together, this should be 24.694633. Let me clean up this 6 a little bit. So when we do this, what we do is we just box all the way to the hundredths place, and we ignore anything behind that. Yep?
I don't understand what you mean when you say which one is precise.
Yeah, so let's say we're measuring things, right? And the top measurement, we're confident all the way out to that last 3. We've got a really, really high degree of confidence out to a very, very small number. The middle one, a little bit less confident, it's less precise. The top one, we can only estimate out to the hundredths place, not any further. So it's basically saying that that's our least precise measurement. our way of measuring that number isn't as good as what we were doing for the top two. So like in lab, I was telling you guys to estimate one digit past the hash marks. That's your least precise digit. Any math that you do from there on out, you can't have it be more precise than that digit. Yep.
So are you counting precision as significant figures or numbers past the decimal point?
Basically, so for example, a hundredths place is more precise than the tenths place. That's
But I mean, like, you're just counting in, like, numbers past decimal, not in significant figures at this point?
yeah, exactly. So in this case, because it's to the hundredths place, we only include two numbers past the decimal. There are tricky situations, though, where you have to do rounding. So, for example, if the number past it is maybe 5 or greater, you can round up. Some physics teachers might teach you error propagation techniques too, but we're not going to get into that as much in this course. So in this case, 24.69 would be your correct answer. Okay. Let's do multiplication and division. So up here we said that the results cannot be more precise than your least precise measurement. With multiplication or division, it's a little bit different. Your results cannot be more or cannot contain more significant figures. Oh my goodness, I can't spell today. Than your number with the least sig figs. And again, let's do an example to show what I mean by this. So let's say I'm taking 23.123.123 and I'm multiplying this by 1.3344. We can plug and chug with our calculator, right? And if you do that, your number that you get out, I think, assuming my math was right, is 4953312. This is the calculator value, but we need to determine how many sig figs to include. So what I do is I look at this number and I would try to say how many sig figs there are. How many are there? Yeah, 8. They're all non-zero. Where with this one, we only have 5, which means our number with the fewest number of sig figs is at 1.3344. That means our answer should only have 5 sig figs as well. So if we count over, we'd say, all right, 1, 2, 3, 4, 5. All of these get counted. Anything after it does not. Does that make sense?
So you go by the one that has the least amount.
Exactly. There are some weird examples, and I'll show you guys. This is the way I remembered it. What's 5 times 5? Hopefully you guys know this. 25. Did somebody miss it? It's a Friday. All right, so 5, we've got 1 sig fig. 5, we've got 1 sig fig. Our answer should only have 1 sig fig, right? So if we look at this, should the answer be 2? What do you guys think? What should our answer be? It's a little bit weird. It's 30. Because if we look at 30, 30 only has the 1 sig fig. Right? So in this case, If you've got a number following that is 5 or greater, you round up. So in this case, it's a little bit weird, but we'd say, you know what, this has 1 sig fig. All right, the counter example that I like to use is 5.0 times 5.0 is what? Still 25. But this one works out a little bit better because here we've got 2 sig figs, here we've got 2 sig figs, and here we've got 2 sig figs, right? So you do have to watch out for these sig figs. They tell you a lot about the degree of confidence in your measurement, and that confidence can be transferred whenever you do multiplication or addition or subtraction.
So you can't just assume that 5 is 5 or 4.
That's a good question. So in this case, let's make a note. These are measured numbers, not absolute numbers, right? So these sig fig rules only count when you're measuring something. If you're doing pure math, please don't say 5 times 5 is 30. Your math teacher will wonder what's going on. But if you're measuring something in lab and you're measuring it out to 5, that means that you're estimating your ones place, right? You're saying it's about 5. And if you're saying about 5 times about 5, that's about 30, right? But if you're saying it's 5.0 times 5.0, you say, I'm pretty confident that it's 25, right? It's basically giving your confidence to your reader. Okay, let's do some more examples, and then I'll give you guys a worksheet for the last few minutes. So let's say we have 40.0 milliliters. So really what this is a density, right? We went over this yesterday in lab. And in this case, assume the 1 is an absolute number. It's not a measured number. The measured number is up top. And I want us to figure out, all right, if we've got 40 milliliters of a liquid, and we know its density is 1.562 grams per milliliter, how many grams of that liquid do we have? How many sig figs in 40.0? 3. We count all of them. We count the zeros that are to the right of a decimal and at the end. So this one has 3. How many sig figs here? 4. Which means our answer should have how many sig figs? 3, right? Okay. If you plug this into your calculator, you're going to get 62.48 grams, right? It's important to remember, too, anytime you're doing multiplication like this, that our milliliters are canceling out, leaving us with grams as our remaining unit. Okay? However, that's not true with, or our 62.48 doesn't follow our sig fig rules, so it should be what? Yeah, 62.5 grams. We want to round up because that 8 is greater than 5. So this must have 3 sig figs. Oftentimes, I do this exact strategy when I'm doing math in the lab. I box my correct answer, but I will show the number from the calculator too, just so that the reader can see it. All right. Let's actually just jump straight into our practice worksheet. And I've got them up front here, so I'm going to hand them out. A few of them are multiple choice, and the rest are kind of short answers. These are really similar to what you might see on an exam, so it's good practice. What I would recommend doing is work with a group. And then after you guys have worked on it for a bit, I'll start going over the answers. So the length of the measured line here, we have to determine that. The hash marks represent what? Yeah, kind of half units, but we don't see a true tenths place hash mark. That means the only hash mark that we have every digit accounted for is actually the ones place. So that means if there isn't a hash mark representing every single place that you want, you can kind of ignore it. You can't really use it very well. So in this case, our ones place, we are confident. That means we need to estimate to the tenths place. That means our answer is going to be 5.7. This is kind of a little bit tricky. But we don't have a hash mark for every single tenths place, so we can't estimate past it. All right, number 2, we've got 13.004, 3.09, 12.947. If we look at the 13.004, we're confident all the way out to the thousandths place. This one we're out to the hundredths place, and then this one we're out to the thousandths place. That means our least precise measurement goes out to the hundredths place. That means our answer should also be the same. So another way of looking at this one only has two digits, right, of the decimal. This one has 3. This one has 3. The one with the 2 digits will win. So in this case, the correct answer will be A. If we look at question 3, it says when performing the calculation 34.530 grams plus 12.1 grams plus 1,222.34 grams, the answer must have how many significant digits?
C.
Well, let's try to stack it up, right? So we've got 34.530. We've got 12.1. We've got 1,222.34. Our least precise one is measured at the hundredths place. So I'm just going to draw a line here and say we can't really count anything to the right of that. We're going to add these all together without even doing the math. Now how many significant figures should we have? So let's just do the math. We've got 1, 2, 3, 5, 6, 6, 7, 8, 5, 6, 7, 8, 9, 7, 0. So this one has 5 sig figs are counted. And then the question is saying 3 sig figs, 3 decimal places, only 1 decimal place, or units of grams cubed. Which one makes most sense? C, only 1 decimal place. So this one's kind of a word problem on top of the math. All right, round the following measurement to 3 significant figures. 9.0985 centimeters cubed. We need to round it to 3 sig figs, so what should it be? So let's use process of elimination. Can't be these two, right? Those don't make any sense. Why do you guys think it might be D instead of A? Yeah, we round up. So the digit past you can round up if it's 5 or greater. So the fact that we've got an 8 right here means we will round up that digit next to it. So this would be the most appropriate answer. All right, next one's multiplication. How many sig figs are in 1.23? Yeah, so 3 sig figs. How many sig figs for this guy? 0.89. 2. So our answer should have how many sig figs? 2. So we can cross out these guys and we'd say those don't make any sense. Now we've got a judgment call. Did anybody check this on their calculator? The answer is 1.0947 if you plug it into your calculator. So if it can only have 2 sig figs, these two, are we going to round up? Yeah, so in this case it would be 1.1 meters cubed. The other thing to pay attention to is because we're multiplying meters by meters, the meters also turn into a cube. If you're adding things, they don't become cubes, so be aware of all the algebraic rules. All right, the next one is a little bit tricky. That 123,000 number has no decimal point shown. So how many sig figs are in it? 3. Because there are no decimal points shown, there are only 3 sig figs here. And then in 3,234, we've got 4, which means our final answer must have how many sig figs? 3. So we can go ahead and look at all of these and we could say, wait a minute, they all have 3 sig figs. What do you guys think we should do here? I would plug it into my calculator first and see what the number is. So in this case, we've got 39778 2000. All right. Now what we need to do is figure out whether or not A, B, C, or D matches this number. So let's express this in sig figs. Or sorry, in scientific notation. I'm going to move this over 1, 2, 3, 4, 5, 6, 7, 8. So we could say, you know what, this number could be 3.97782 times 10 to the 8th. However, that needs to be changed to 3 sig figs. So we'd have to change this to 3.98 times 10 to the 8th. That trims it down to the correct 3 figs, or the correct number of significant digits. And if we go over here, we can say, hey, that matches B. It's obviously not going to be C. That doesn't match our measurement at all. If we look at A, that's also not quite right. And if we look at D, that's a super duper tiny number, so that doesn't make any sense. Does that make sense? I think what I'll do is I'll let you guys continue working on this, and then when we come in on Monday, we'll go through the answer key, and then we'll do a little bit more review on unit conversions. Make sure you guys start sapling. Try to log in, get going. I really recommend doing some of the tutorial activities too, just to familiarize yourselves with it. If you guys ever have questions with sapling, email me and tell me the number that you're stuck on, and I can actually pull up your homework assignment and see what you've attempted.